Okay, so today is week 4. I'm going to do homework homework 3, question number 8 on sandwich material and shearing stress, because I did not really show when it is sandwich material how to handle a problem like this. I did not show that in class last week. So, but it's on the homework already. I'm going to show you how it's done. And Lux asked me if you take different material as a reference material, will your answer still be the same? The answer is yes. And I'm going to show you based on this example. Okay, homework question number 3, question 8. Then we are going to look at in the equation of shearing stress distribution. Okay, we're going to form the shearing stress distribution equation. Then we're going to look at longitudinal shear of a beam section. Over here is where you start looking at failure analysis. Okay, we start going into failure analysis down here. So it's not an easy topic, okay, but it's possible with the rules that I gave you, the four rules. And then finally, I hope to finish off in shearing stress in thin wall section. I've already posted homework for week 4, okay, and we'll go from there. On Thursday, you will have a tutorial, okay, as usual. Okay, let's look at this question. So this question over here is, in fact, the solution has been posted. Okay, we'll just approach it differently, but the answer will be the same. So this is example 1, and it's going to be on homework 3, question number 8. Okay. So a steel bar and an aluminum bar are bonded together as shown to form a composite beam. Knowing that the vertical shear in the beam is 4 kilopound force, and that the modulus of elasticity for for steel is 29 times 10 to the power 6, and for aluminum is 10.6 times 10 to the power 6 psi for the aluminum. Determine the average stress at the bonded surface and the maximum shearing stress in the beam. Okay, so what we have is, if we were to, I'm going to address the transformation. So if this is our y and this is our z, okay, so the shearing force is coming down, right? So V, and this V happen to be at 4 times 10 to the power 3 pounds of force. Okay, so part A of the question is to ask what is the average stress at the interface, okay, or on the bonded surface, and the maximum shear stress in the beam, and this should be at the centroid. Okay, so we know that the formula we're going to apply. So let's look at some geometries. The width, okay, is 1.5. Okay, the steel is 1 inch thick. The aluminum have the same width of 1.5 inch and 2 inches thick. Okay, so the formula that we're going to apply is a shear stress, right, is equal to Vy over Izz Qz divided by T. Okay, and then we are going to apply. Okay, I'm going to get the 4 rules from the tutorial. Okay, we're going to apply these 4 rules. Okay, these 4 rules again, right, where V and I are constant, the geometric datums at the centroid, analysis starts from Y max, first moment of area cannot intersect the centroid. Okay, so those are the 4 rules that we're going to comply and then solve this problem. So for this case, it's a sandwich material. We have to find the reference we have to not find, but we have to determine what is the reference material that we want to use. So we know that given that the Young's modulus of aluminum is equal to 10.6 10 to the power 6 psi, and the Young's modulus of steel is 29.0 times 10 to the power 6 psi. Okay, and we are given that the shear force is at 4 times 10 to the power 3 pounds. Okay. So I'm going to decide using steel. Okay, using steel as the reference material. Okay, so if I go into the solution manual, so I posted the solution, I think, and let me find it. Documents, not this document, but so this is homework number 3, right? I posted the solution already, which you all can get online. But I want to do a different approach, and I want you all to have the confidence that when you select different material, your answer should be the same. Okay, and does not matter what reference material you choose. Okay, so I'm going to put this here so you can see, okay, or check some of the numbers, right? So if you look at the solution manual, okay, I'm not going to go into detail. They pick the reference material as aluminum. Okay, whereas we can pick the reference material as steel. Okay, so once we make the decision to pick the reference material for steel, we can find the N for steel is equal to Young's modulus of steel over Young's modulus of steel. So this is equal to 1. The N for aluminum is Young's modulus of aluminum divided by Young's modulus of steel. So this turned out to be 10.6 divided by 29. So this will become 10.6 divided by 29 is equal to 10.6 divided by 29. I do in fraction form. So it's 53 over 145, right? Okay, so we make the decision to use steel as a reference material. So by looking at the shearing stress equation, okay, we have to find IZZ, right? We have to find IZZ, and we have to find the centroid. Okay, so the next thing we have to do is find the centroid. Okay, find the centroid and IZZ for the sandwich material. Okay, so I'm going to have 2 sections. So one is for aluminum, and the other one is steel, right? Then we are going to put in our N, right? So for aluminum is 53 over 145. For steel is equal to 1 because it's our reference material. And from here, we're going to have our N width multiplied by depth. So for the aluminum, it is 53 over 145. The width is 1.5. the depth is equal to 2. Okay, so 53 over 145 times 1.5 times 2 is equal to 159 over 145. And for the steel, right, 1, the width is 1.5, the depth is 1, so this is equal to 1.5. So if we take the summation, right, so 159 over 145 plus 1.5, that would be 753 over 290. And then next we're going to find the individual centroid. Okay, individual section centroid. So I'm going to pick the datum. Now this is finding centroid, okay? So I'm going to pick the datum from the top. This is a small y bar. So this is equal to 2 divided by 2, which is equal to 1. So this is 2 plus by 1 divided by 2 is equal to 2.5. Okay. And then I'm going to multiply them in our last column. So n omega or with y bar. So this is 159 over 145. So 1.5 times 2.5 is equal to 3.75. So 159 over 145 plus 3.75. So this is 2811. Okay. So the y bar, okay, is equal to 281 over 580. Then we divide by 753 over by 290. So 2811 over 580, 2811 over 580 divided by 753 over 290. So it's equal to 1.866, 1.867. From the top, inches from the top, and all, okay, all, right? So 3 minus 1.867, 1.113 or 133 inch from the bottom. Okay, so if we look at the solution, what is theirs? Okay, so it's the same. Can you see here? This is from the bottom, right? 1.133, 1.867. As I said, their reference material is what? Is different from ours, is aluminum. Okay, so I want you to have the confidence, okay, to look at this. So to look at, regardless of the reference material you take, the answer should be the same. Okay, but you have to be cautious in some sense. Okay, so next, so for our case, we took stainless steel as steel as a reference material. So we're going to find the I, the second moment of aluminum, and the second moment of steel. Okay, so I of aluminum, right? So it's equal to 53 over 145. Multiplied by width is 1.5. 2 squared divided by 12. So it's the same as composite material in bending, right? The second moment of area is still the same. So this will be equal to 159 over 145. Then you have 1.867 minus 1, the whole thing squared. Okay, so 33 over 145 times 1.5 times by cube, not squared, sorry, to the power cube, divided by 12 plus by 159 over 145 times by 1